Okay, so before we get started today on the next section in our journey through chapter 24 on Gauss's law, just a reminder that we're going to have our first midterm next Thursday, covering the first three chapters, right? The electric force, electric field, and then right now we're on Gauss's law, which is just a way to calculate the electric field or a charge distribution. Actually, you can do either side of the equation in these very symmetric systems where you can actually create these things called Gaussian surface, which we'll talk about in a second here. So that's next Thursday. It's in class. There's 3 questions, 1 from each chapter. Okay, so those of you who had me before will know what that's about. Those of you who are incoming from a different class, either ask your classmate or just come by my office hours, talk to me after class, and then I can kind of give you guys a fair playing field, right? Because I think a lot of the students who had me last semester kind of already know what to expect from the midterms. Okay. On Monday, the next Monday, I'm going to devote maybe 30 minutes of the lecture to doing some review, just going over the material and maybe going over some of the questions you guys might have. Yeah, questions back?
For the midterms, do you allow a cheat sheet?
No. So I give you a formula sheet, and those are all the formulas that I think you should need. If there are additional formulas that you need, you can ask for it in class, and I'll give them to you, but they may not be relevant. Okay. So so don't try to memorize equations, but understand what they're for. Okay. So that's usually the crux of the thing. Okay. And so for Monday's review, I made a little discussion on Canvas and asked you guys to just post your top question from each chapter that you want to ask, either on the concept, example, or one of the homework problem, or one of the worksheet we worked on, right? So we can, and whichever one, I think, I'll look at that on Sunday. I think I made it due like Saturday night or something like that. Not due, but like, and put it on your to-do list by Saturday night. I'll look at that on Sunday, and then on Monday I'll talk to you guys about the ones that are the most important. That way I get some idea of what you guys think are the most important thing, and then I'll get my interpretation of what's the most important, and you guys can figure out, how to, maybe focus your studying for the midterm, okay? All right, any questions before we get started on chapter 24.4? Okay, so next section is sort of where all the stuff I've been talking to you guys about this whole week, basically, right? So I talked to you about this idea of symmetry, right? Where there's certain symmetry. So like, if a stick like this, then it's translational symmetric. If it's a plane, and if you're pretty close to the surface of the plane, no matter where you're on the plane, it looks exactly the same. It's, imagine you're just walking in a desert, right? It's, there's nothing around, so no matter how far you walk in the desert, it looks the same to you in every direction, right? There's also cylindrical symmetry, right, where things are the same as you rotate around, okay? And the spherical symmetry, which is the highest symmetry, where you can rotate in 3 dimensions and the sphere will still look the same, okay? So what we're going to do is we're going to apply this plus this idea of flux, which we learned last time, to figure out how we can calculate electric fields or charge distributions using this idea of Gauss's law, okay? So remember the first thing we talked about actually in the introduction of the chapter, right? We had this idea that, if I have some opaque box and I notice that, there's some electric field going towards the box, right? Just by, measuring the electric field from outside the box, okay? Somehow, right, we can deduce that there's some sort of negative charge inside, right? Because if there's the negative charge, right, maybe some electron in here, right? We know that negative charge always have electric field pointing towards it, right? But if we have a positive charge inside that box, right, we can actually predict that there's going to be some electric field going out of the box instead, okay? And these field lines going through these boxes, these surfaces, is what we call electric flux, right? These are specifically electric flux, okay? Usually denoted by this capital phi with a lowercase e. So that's what the book does, okay? And we're going to use this to basically figure out a mathematical relationship between, right, what we just learned about called flux, and how to figure out how much charge is inside. And this is where this magical number called epsilon naught come in. And this is why epsilon naught is a better constant rather than that capital K we have for the Coulomb's law. Okay, so I'm just going to give away the mystery. So the relationship between the electric flux, which is the stuff we just learned how to calculate, right, is actually just whatever the charge is inside that box divided by this constant epsilon naught. Okay, it's the equation's as simple as that. Just ignore the stuff between them. Okay, for now. Okay, if I can figure out how much flux is going through this box, I can figure out how much charge is inside that box. Okay, and and when I was taking this class, I didn't realize I don't want to say the word like magicalness of this, but this is like a crazy thing, right? So you measure, you never look at the charge, you never even touch the charge, you never have to open the box, but by just measuring what's the field going through the surface of the box, or just you never have to go inside, right? You can be right on the edge of the box, measure this electric field, right, and then calculate this electric flux, and you can actually figure out what's inside that box. Okay, it's like a little. If you can do this with cards or something like that, you can actually tell the numbers on the cards on the other side. That would be kind of I mean, if I can do that, I wouldn't be teaching here. I'll be off, just going to casino once in a while and then just living my life, right? Okay, so this is known as Gauss's law. Okay, it's kind of a fantastic thing. Okay, so let's take the point charge as an example. Just see what happens. Okay, what I'm going to do, right? Gauss's law tells me that, right, the electric flux is going to be how much charge is inside divided by this epsilon naught thing. Okay, this simple equation is hiding a lot of stuff, but let's just do this simple example, right? Where let's say I have some charge, point charge q, lowercase q, right? And I want to figure out the electric field, a radius r around it. Okay. Actually, from chapter 23, we know the answer, right? We're just going to double check the answer. The electric field is actually 1 over 4 pi epsilon naught, the amount of charge in the center divided by r squared, right, in the r hat direction. That's from chapter 23. We already know what that answer is. Okay. So let's see if we can figure that out using Gauss's law instead. Okay. So let's do let's do the left-hand side. The left-hand side is the flux, right? How do we calculate this flux? Right? Remember the electric flux, right? It's basically how much electric field is passing through some surface. Okay? What I'm going to do, since we're trying to figure out what is the electric field at some distance r away from the charge, I'm going to draw this thing called a Gaussian surface. This orange thing here is known as the Gaussian surface. Okay. On the board, it kind of looks like a line, but just imagine I just enclose this with a sphere, an orange sphere around it, a big orange ball around that charge. Okay. Okay. So, and it has some radius that has r, right? That's the variable we're going to try to figure out. Okay. So in that case, okay, if I want to calculate the flux, it's going to be this E dot dA thing, right? Which is the the complicated, crazy dot product with the integral equation I try to hide from you. Okay. And this circle here, right, just means it's an enclosed surface. Okay. So this surface has to be closed, right? Because what's going to happen on the right-hand side, you have to enclose all the charge. If if you're missing one side of the box, then it's not enclosed, so the charge can get in and out. right? It's kind of, you have to enclose all the charges, okay? But since you can pick what the surface is, right? You can decide what shape the box is. In this case, I'm picking a sphere with a radius r, okay? All right, a hollow sphere, okay? Okay, so we have this gnarly equation here, right? But from the symmetry of the problem, right, since we have a charge at the center, right, we expect the magnitude of the electric field to be always the same, right, on that surface, right? So therefore, the electric field is constant in magnitude at least, right, on the Gaussian surface. I'm just going to call it GS, right, G dash S. Who's not having a happy time erasing things? Okay, just delay in erasing, okay? The other thing is that, well, remember the idea of flux is that you want to think about, right, on this surface, there's some normal vector at every point here, right? But we know that from the symmetry of the problem, right, the electric field and that normal surface direction is always in the same direction. They always line up, right, no matter where you are on the sphere, right? They follow each other. So, therefore, the angle between them is always going to be 0, right? Therefore, what you can do is you can compute this dot product, or simplify this dot product, by just taking the magnitude of the electric field, right? Let's do that, right? Times cosine of this angle theta, right? dA, that's what this dot product breaks up to. We know this is a constant on the surface. We also know that theta is always 0, therefore cosine of 0 is always 1, right? So therefore, this actually simplifies to, right, if there's something you're integrating, it's just a constant, you can pull it outside the integral, okay? Right? And then cosine of 0 is just 1, so I don't even need to write that, okay? And now we are just calculating the closed integral, some enclosed surface integral of an area, right? And remember when you do this type of integral, right? Right? When if I just integrate dx, right, you just get x, right? Right? If I integrate dA, I just get a, right? Okay? So this is just E times the area, okay? All right. So the surface area of a sphere, right? That's the area. So that's because my Gaussian surface is some sphere. The surface area of a sphere, right, is 4 pi the radius square, right? Okay. I'm using the little r here because I declare that the sphere has to have a radius of little r. Okay. All right. So that's the left-hand side, LHS. Make sure it denotes that. Okay. The right-hand side of Gauss's law, this is LHS, this is RHS. The right-hand side of Gauss's law is just the amount of charge that's inside my sphere divided by epsilon naught, right? So the right-hand side, right, the amount of charge I enclose, since I only have one charge, is just Q, right? And then you have to divide by epsilon naught, okay? Okay, equating the left-hand side and right-hand side, that means E, the electric field strength, 4 pi r squared, is going to be equal to Q divided by epsilon naught. I'm not going to do that yet, okay? This is the, let me go over here. Unfortunately, of course, I put the left-hand side on the right-hand side in like this, okay? Hopefully that makes sense. Okay, right, solving this equation for E, right, is just 1 over 4 pi epsilon naught Q divided by r squared, right? Right, and that's exactly the same answer we found from chapter 23. Right? Yes, go.
Left-hand side, right-hand side, we're talking about the equation for Gauss's law.
Right. This is the left-hand side of Gauss's law. The right-hand side of Gauss's law is this. Okay? Exactly. Thanks for that clarification. Okay. Right. The only thing that's missing, right, is the direction, right? But the direction you can figure out from the drawing, right? You don't need to do a bunch of math to figure that out, right? It's going to be pointed outward or in the r hat direction, right? Okay. So this is kind of cool because, right, you know, somehow we actually, technically we just derive, you know, not just this particular electric field, we actually also derive Coulomb's law, right? Because if you multiply this electric field by some test charge Q prime, then you actually get the electric force, right? And you actually just derive Coulomb's law. Okay, so just note one more little caveat, just to think about the geometry a little bit more, right? Right, since we have a point charge in the center here, right, the electric field line kind of fans out in all directions, right? If I have a sphere around this electric charge, right, let's say with some r small, some small radius, right, this surface has a smaller area, right, compared to if I have a bigger sphere r big. Does that make sense? Right? Right? Then you would think, wait, wouldn't that mean if I have a bigger surface, I would get more electric flux, right? Right? The bigger your surface, the more flux you'll get, right? The problem is that, right, with an electric field line coming out like this, the same number of field lines impinges through the small and the big, right? So basically the electric field density goes down as further away you are, which makes sense. The electric field strength goes down the further away you are from a charge, right? And therefore, the two actually are balancing each other out, where the electric flux, okay, through the small sphere, okay, is actually exactly the same as the electric flux through the big sphere. That's just an interesting geometric fact, okay? The electric field goes down as r squared. The surface area of a sphere goes up as r squared, so the two actually exactly balance each other out. Right? It's sort of magical that way. Right? Let's talk about what happens if we have a charge outside our Gaussian surface, right? And the book uses this example here, but you know, this can be used for any shape where you have your charge, instead of being inside your Gaussian surface, now we're going to redeclare our Gaussian surface as this. I don't even know what this is. It's like a wedge of a pineapple or something like that. I don't know. Okay, so this orange thing, right, is our Gaussian surface now. Okay, right. If we have a charge that's outside that Gaussian surface, right, the normal vector for the on this side, okay, is actually pointed towards the electric field, so it actually gets a negative flux, right, on this surface. Okay, the electric field line passes through our little object here, right, but on the other side, right, you have electric field line and the area vector now pointing in the same direction, right? So the flux here is negative, right? The flux up here is positive, okay? If you add up all the different fluxes, right, guess how they're going to be related to each other, right? Well, if you add up all the negative flux and all the positive flux, if you add them together, they're going to add up to 0 because there's no charges inside the surface, right? Right? If there's no charges inside the surface, Gauss's law tells us that the electric flux is 0. Okay? Okay. That's another neat thing about it. Okay? Well, what if you have more than one charge? Okay? Let's just dive into this problem even a little bit more, right? What if we have multiple charges, not just one, right? Okay? Let's say I have a bunch of charges, you know, around here, a bunch of charges outside, okay? I'm going to declare my Gaussian surface once again as this orange, you know, surface, right? So, if you have multiple charges inside here, okay, Gauss's law tells you that the electric field, right, the electric flux It's just whatever the amount of charge that's inside divided by epsilon naught, okay? So let's say I have, you know, some Q1, Q2, 1, 2, 3, 4, 4 positive charges, okay? Right? That's actually 4 times Q pluses. Let's say, I mean, the book doesn't do this, but let's say the magnitude of these plus charges and the minus charges are the same, right? So there's 4 plus charges, okay? And there are 4 minus charges, right? If Q plus is equal to negative Q minus, right? This actually gets you a net charge of 2 Q pluses, right? Right? So when you're adding up the charges inside that surface, all you have to do is just add up the charge. Okay? The charges that are outside, right, does not contribute anything to the electric flux. All right? Any charge that's outside your Gaussian surface will give 0 electric flux, okay? Right? Because any flux that's created by, let's say, this charge, right, enters here, but then it exits over here, right? So this will give you the negative flux, this will give you the positive flux, and you end up with a net flux of 0. Okay? So therefore, right, if you want to figure out the net electric flux of multiple little charges here, right, you can actually calculate the electric field from one charge, right, dotted into this surface that could be very complicated, right? But usually we're just going to use a sphere or a box or a cylinder, okay? Plus the electric flux through, you know, due to charge 2, the electric flux due to charge 3, and so on and so on and so on like that, okay? And that allows you to calculate the total electric flux. It's kind of like what we had before when we talk about energy, right? If you have energy from kinetic energy, you have potential energy, you have static, elastic energy, right? You just add them all up, okay? And this is nice because, right, these are scalars, right? They're just numbers, right? You don't have to deal with vectors. There's no x and y directions, okay? So therefore, right, the electric field total, right, it doesn't have the word total in it, right? Whatever electric flux you calculated from all these different electric field, right, they just add up to all the little charges that you happen to enclose on that surface, okay? Which is nice. And so this is the general equation to calculating, well, this is basically just Gauss's law, right? And usually what I do is, I mean, I taught this class probably too many times, so I actually memorized this entire thing. But the thing you want to remember is that, right, the electric flux tells you how much charge is inside that surface divided by some constant, okay? And if you, and I'll give you this constant. I'm not going to force you to memorize this constant, right? 8.85 times 10 to the negative 12, right? So it's just some constant, and the reason this constant is here is actually just it's almost just a unit conversion factor, okay? So let's do a little Q&A thing here, right? So let's look at these 5 different diagrams where we have some point charge in the middle. Some of them are bigger than the other, right? This is 2Q, this is 2Q, this is regular Q, okay? Can we figure out which of these has the biggest electric flux? Okay? Right? Okay. And Gauss's law tells you that the electric flux is this complicated integral thing, right? Which eventually equals to just the amount of charge inside that surface divided by epsilon naught. Okay? Anyone thinks it's A, well, B and A, meaning this one and this one has the biggest electric flux? Anyone thinks that? Okay. How many of you guys think it's B that has the biggest electric flux? Because it has a smaller circle. 3? Okay. A little contest here. How many of you guys think it's B and C? The 2 charge version, 1 charge with circle, and then the rectangular one. Okay. How many of you guys have thinks is B and D, right, where you have a 2 charge one, a 1 charge one, right? That's B and D. Anyone thinks it's that? Right. How many of you guys think it's B and E, whereas this one and this one? Right? Okay, you change your mind, great. So that's about, I think about 8 of you guys. Okay, so in fact, it is B and E, right? And the way you want to think about this is that I'm asking you about which one has the biggest electric flux. Don't worry about the stuff in here, right? I know this equation to be true no matter what, right? So all I have to think is that, well, which of these surfaces encloses the most charge, right? It's the one that has twice the charge versus the one charge version, right? That's all I have to think about. It's very simple. Okay, this one has 2 charges, this one has 2 charges, therefore it has to have the biggest electric flux. No matter what the surface is, I can draw an amoeba around this and it will have the same amount of electric flux, okay? Okay, so let's do a couple examples on using Gauss's law, okay? So one thing to be careful about Gauss's law, it only applies on closed surface, right? Remember, if I don't have a closed surface, right, oops, right? Let's say this is an electric charge, right? If it's not a closed surface, I can sneak a charge in and out of there, right? That changes everything, right? You don't want that. So you have to close the surface so you cannot sneak a charge in and out of your box, okay? And these are known as Gaussian surfaces. So those are all the orange surfaces that we've been looking at, okay? So one thing to note is that the Gaussian surface is not a physical surface. It doesn't have to be real, right? Remember up here? Right. This orange surface doesn't have to be a real thing. It's just something you make up. You can pick whatever surface you want. You decide what surface you want to calculate this electric field on. Okay? But what's important is that this Gaussian surface is an imaginary physical thing. Okay? Okay, so the other thing is that you cannot find the electric field from just Gauss's law alone. Okay? Remember when we did the point charge? We needed the diagram, the drawing, to figure out what the direction is, right? Gauss's law gave us the magnitude. It doesn't give us the direction, okay? And so you have to use symmetry and this idea of superposition, meaning, right, if you have multiple charges inside your Gaussian surface, right, you're going to add up multiple electric fluxes, okay? All right. So let's see if we can do an example here. Okay, so let's do the electric field outside a sphere of charge as opposed to just a point charge, right? I'm going to set up the problem, right, where I have some object, right, that's going to have maybe a bunch of plus charges around it, okay? Plus, 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 plus. Okay, and these plus charges are uniformly distributed on my little sphere. Okay. Okay. All right. Let's erase this little circle here. There's no reason for that to be there. Okay. So this is uniformly charged. So there's no special place on the charge. This will be important for the next part, not this part. Okay. All right. And we're tasked to figure out what's the electric field outside the sphere at some radius lowercase r, okay? All right, this is going to look a little bit repetitive, but we're going to see that there's actually a slight difference if we try to go inside the sphere, okay? What I'm going to do, first thing I'm going to do, is I'm going to think about, okay, what Gaussian surface will respect the same symmetry as this charge distribution, right? We have a sphere of charge, so we want a spherical Gaussian surface, right? So I'm going to draw a sphere, right, around it, right? I'm not going to shade in the rest of it, but this is kind of like the edge of the sphere. Right, just kind of like a 2-dimensional projection. I'm going to make this sphere have a radius r because we are interested in what is the electric field at some radius r away from the center of that charge. Okay? Okay? Because this is what we're interested in, right? Oops. I need that to be orange. right? I can't change color for some reason. There you go. This is what we're interested in calculating, right? Okay. So I'm going to write down Gauss's law. Okay, this is where we're going to try to solve, make the concept connection that we're going to do the symmetry and utilize Gauss's law to solve this problem. Okay, Gauss's law just tells us that the electric flux is the amount of charge that's inside divided by this constant called epsilon naught. Okay. Okay. So the electric flux through this surface, right? Since we can justify that, well, it's going to be a constant, right? Because they're all equal distance away from the center of our charge distribution. Okay. So therefore, right, if we try to compute this integral, right, we know that this is a constant magnitude, just like before, right? And also, the surface vector, n hat, is always in the same direction as E, right? Right? So cosine of theta is equal to 1, right? So once again, with this justification, right, we can do this integral. We have to do this closed surface thing, right? It's E cosine theta dA, right? We know this is a constant, so we can pull it out. We know cosine of theta is equal to 1, right? So it's actually E, the surface area of dA, and we already know that that's just the area of our sphere, and the area of a sphere is 4 pi r squared. Okay, so once again, we already took care of the left-hand side, right? The right-hand side, right, just wants us to calculate how much charge is inside my Gaussian sphere. Okay, the problem tells you that the total charge of this Gaussian sphere has a charge Q. Sorry, Gaussian sphere. Of this solid sphere has a charge Q. Okay, therefore, how much charge is enclosed inside my Gaussian sphere? Is it part of Q, or is it some fraction of Q, or is it all the Q? Right, when I made this drawing, how much of the charge did I enclose inside? Anyone? All of it, right? So, right, so I got all the charge, so the right-hand side is actually pretty simple, right? Qn is just the total charge of the sphere, right? Or, if you divide by epsilon naught, you get that. So equating the two sides of the equation once again, right? The electric field 4 pi r squared is equal to just the total charge of the sphere over epsilon naught, right? And therefore, the electric field is actually, I can do fraction, right? The total charge 1 over 4 pi epsilon naught divided by r squared, right? Right? Looks very similar to the point charge, right? Right? This is one of the cool things about it. If you have a spherical charge distribution, right, and you're outside that distribution, you can pretend that all the charges is actually at the center of your sphere. Okay? So neat. But what if you want to try to figure out the electric field inside my little bowling ball, charged bowling ball? Okay? So I'm going to draw a bigger version of it. Okay? And you have a bunch of plus charges everywhere, right? We always just assume that the charge is plus, and if we happens to be doing negative charge, we'll just reverse the sign at the result, right? But now, right, we're interested in the electric field inside the sphere, so we want a Gaussian surface that's actually inside the sphere. Remember this Gaussian surface? It's just an imaginary thing. You can imagine it to be whatever you want. Okay? I can imagine it to be, the crazy hair that I have someday when I wake up, right? But that's going to be really hard to calculate, all those all those dot products, right? A sphere is nice because I know how to calculate that dot product pretty easily, especially one that respects the symmetry, right? So this little sphere inside is just imagined, okay? And the electric field, once again, it has this spherical symmetry to it, right? The electric field also have to obey that spherical symmetry, right? Right? And at every point here, right, this also obeys n hat, Okay, so now we need one more variable. We need to know the radius of the big sphere. I'm going to call that big R. Okay. Okay. So big R is the radius of the physical charge ball, right? Little r is just my imaginary Gaussian sphere. Okay. Okay. So we're going to apply. So this is some of the setup. Okay. I'm going to skip to the solve part, right? Well, we're going to apply, right? Once again, Gauss's law to solve this. Okay. Qn divided by epsilon naught. Okay. This left-hand side is exactly the same, right, as before, where it just happens that little r is smaller than big R in that case, right? It's the same thing, right? We're just calculating, you know, this constant electric field justification, and n hat being in the same direction as the electric field gives you that cosine of theta equals to 1. All of that still holds, so therefore, right, the left-hand side is still the magnitude of the electric field 4 pi little r squared. The right-hand side is actually the harder thing to calculate in this case, right? Because that's actually the fraction of charge that you have enclosed inside my orange sphere, but not all of it, right? Some of it is actually outside. Remember, the charges that are outside your Gaussian sphere does not contribute to the Q inside, right? Because that's why it's called Q inside. Okay, so now we have to figure out what fraction of the charge is actually inside versus outside the sphere. Okay. Okay, so in order to do that, right, we have to figure out what is the charge volume density, right? There may be a smart, you know, a fancier way to do this, but I'm going to do this kind of the long and analytical way, right, in order to do this problem the same way no matter what we end up with. Okay, the volume charge density, remember that has the symbol rho. Okay, the volume charge density is the total charge of that sphere divided by the volume of the big sphere, okay, of the charge. I'm even going to note that down here. Okay. Okay, well, the volume of a sphere, anyone know that formula? R to the third, right? Exactly. Okay. In this case, I'm using the letter big R because it's the volume of the charge, not the volume of the Gaussian surface, right? So you have to be careful with your different R's, okay? Right? So the charge density is actually Q 4/3, oops, upside down, 3/4 pi divided by R to the third, okay? That's the charge density, okay? I'm going to do is this little technique where I'm going to pretend I'm going to integrate from r equal to 0 to r equals to little r, right? The variable we're integrating are little thin, little concentric spheres, hollow spheres with a thickness dr, okay? Okay. And that will allow, if I can figure out the amount of charge that's on here, right? If I add up all the little concentric spheres, then I can get the total charge that's actually enclosed here up to this orange line, okay? I don't want to go out to the black line. I only want to go out to the orange line, right? Because going to the black line, you know, gets me all the way, because I want to figure out the electric field inside the sphere, not outside, right? Okay, so the amount of charge that's inside, oops, yeah, let's just do that in purple, it's fine, right? It's basically the integral of the volume inside, right? The volume of the Gaussian surface not the big sphere, the solid sphere, okay, times whatever that density happens to be. Okay. Okay. Right. The density is actually a constant, right? Because this big R, right, does not change with my little r. Okay. Right. So I'm going to plug that over here. 3/4 Q. There's a pi on the bottom. There's an r to the third on top, on the bottom. Okay. So how do I do this little volume integral? Okay. So these are constants, so you can put it in front. 3/4 Q pi r to the third. Right. There's a pretty smart way to do it. Well, I'm just trying to remember that dv, right? Just like when you integrate dx, you end up with x, right? You integrate dv, you end up with the volume. But in this case, what volume are we talking about? Volume of the charge or volume of my Gaussian surface?
Gaussian.
The Gaussian surface, yeah. Okay, that's actually the r to the third. This is the volume of the Gaussian surface, okay? And therefore, 3/4 Q pi r to the third, right? The volume of the Gaussian surface is 4/3 pi little r to the third power. Whew. Okay, so this is actually kind of nice because the 4 cancel out with the 4, 3 cancel out with 3, the pi cancel each other out, right? So Q enclosed, let me go back to purple, Q inside, which is all this calculation was about, right? It's just Q r to the third and then r, big R to the third, okay? Okay. Now we're going to combine, so this is the right-hand side of the equation, right, if you divide by epsilon naught. The left-hand side I already figured out, okay? Left-hand side was E 4 pi r squared. The right-hand side is this complicated thing, Q r to the third, r, big R to the third, right? Let me just push this down a little bit so we have some space. Okay, so solving this equation for E, okay, this actually cancels out mostly, right, is, oops, of course the right-hand side, right, is there's also, you divide this whole thing by epsilon naught, right? So there's actually an epsilon naught down the bottom, okay? Because we actually want this divided by epsilon naught, divided by epsilon naught, and so on with that, okay? Because that's the right-hand side, right? I just forgot about this factor here. Okay, so it's 1/4 pi epsilon naught, the charge times r, right? Because not all three factors of r cancel out, divided by r to the third, okay? Right, so the electric field inside is different from the electric field outside, okay? So the neat thing about it is that if you're inside here, the electric field actually increases as you go out further linearly, right? Because, right, it actually grows as r, okay? When you're outside your black charge distribution, it falls down as 1/r squared, just like a point charge, okay? So you can actually plot this, okay? If you plot the electric field on the x-axis as a function of r, and let's say this is big R is the radius of the sphere, okay? The electric field actually grows linearly and then goes down as 1/r squared, proportional to r, okay? That's sort of cool, okay? Right on the edge there, there's going to be something funky happening, okay? Let's stay off the edge for now, okay? It's actually a right? It's not a differentiable function, right? Because there's a cusp there. Okay, any questions about this? All right. There's a couple of other examples that that's in the textbook, so really recommend you guys go through those. There's one that's on a cylindrical symmetry version of it, right? How do we calculate electric field? We have to have cylindrical symmetry, where your Gaussian surface is now a cylinder versus a sphere, Okay, you have to calculate the surface area of a cylinder instead. Okay. There's also one with a plane of charge. This is actually kind of confusing because you have this plane, right, symmetry, but you're going to construct little cylinders near the surface of that plane still. Okay. The neat thing is that because the reason you want to do that is because you just want these flat surfaces on top where the electric field and your area's normal vector points in the same direction. So when you do the dot product, you end up with 1. Cosine of 1. Cosine theta equals to 1. Okay, let's see. I'm going to introduce the next section, but we probably don't have time to finish it up. Before we do that, any questions on using Gauss's law? So definitely go through all 3 of these examples, right? Or go through the sphere one yourself again, do the cylindrical one, do the plane one. Okay, those are always going to be some sort of problem that you will run into in a class like this, where the symmetry actually helps you a lot in, doing a lot of the integrals. Okay. I mean, technically, I didn't even do any integrals, right? Well, what's the integral of volume of something? It's just the volume of that object, right? Okay. Now, we are actually pretty well equipped to talk a little bit about conductors and insulators and how they behave under this condition called electrostatic equilibrium. Electrostatic equilibrium means once you kind of set the object, you have a certain amount of charge on a system, where do those charges kind of actually rest after you wait a while, okay? And for electricity and magnetism, a while means like maybe a nanosecond, because the charges actually moves around pretty fast, okay? So remember, when you have an insulator, let's just do the rod situation, right? The charges cannot move around, okay? Right, let's say I have a bunch of plus charges here, right? Even if I have more plus charges on this side and fewer plus charges on the right-hand side, an insulator does not allow those charges to move, right? That's the definition of an insulator, okay? But for a conductor, the charges are free to move around. So what I'm going to do is I'm going to put a bunch of plus charges on one side, right? But what's going to happen is that these plus charges are actually going to repel each other. So this plus charges is going to try to get as far away from this one as possible. It's going to move, okay, because you can move, okay? So in electrostatic equilibrium, so maybe after like 1 nanosecond, right? Okay. What's going to happen is that these charges are going to move as far apart from each other as possible, right? But they cannot jump off the conductor, right? Because they cannot jump into air, because air is actually an insulator. So what happens is that these charges will actually rest on the edge of this conductor. Okay. Right. Let's not even draw the charges there. Okay. Does that make sense why it happens? Right. These plus charges, right? If you have 2 plus charges next to each other, they're going to try to repel each other, right? Okay. So they're going to try to repel each other as much as you can. When you get to the edge, they cannot jump off the conductor, therefore they just stay at the edge. Where in an insulator, right, those charges are held in place by the atoms. So therefore, even though they have electrostatic stress on them, they cannot fly away from each other, right? Because that's the definition of an insulator. The charges are not free to move around. Where a conductor, did I say the opposite? The definition of an insulator is that the charges are not free to move around in that material, where on a conductor they are. So they're going to move as far away from each other as possible. Okay? It's as if I have a intro physics class, right? And and all of you guys are repellent to each other. You're going to sit as far away from each other as possible in this classroom, right? Okay? Where if I have assigned seating, right, like an insulator, I'm going to force you to sit in those places, okay? So that's the 2 examples, okay? So we're going to talk about that a little bit tomorrow, and then we're going to do a worksheet dealing with Gauss's law in a very interesting example. Okay, so wrap up today, and we'll see you tomorrow. Stop recording.